there's actually two types of improper integrals. The type you guys talked about in class, and I think the only type that's in your book is the type where one of the limits or both of the limits are some sort of infinity. So if you see an infinity in your limit of integration, automatically we know it's improper. The other type of improper integral, which I don't think we actually deal with this with that type in this class, I'll just write down one of them, is an integral like this, like the integral from 0 to 1 of 1 over the square root of x. This one's improper because the function 1 over the square root of x is undefined at somewhere in the interval. So that's also improper, but I'm not going to cover that today because I didn't see it in your textbook, I didn't see it in your homework, and I didn't see her talk about it in class. Those seem like 3 good reasons to not talk about it. So if it comes up next week, I will certainly bring it back into play. But I really, I'll check with my colleagues too. I'm pretty sure that type of improper integral does not get addressed in this class. So we shouldn't spend time talking about it if it's not something you're going to have to worry about. Also, let me change a video setting here. There, hopefully the board is easier to see now. Okay, so this first example here is kind of the classic example of an divergent improper integral. So an integral is said to diverge if you have an infinite amount of area. So here's how we do it, right? If you've got the integral from 1 to infinity of 1 over x, whenever you have an integral with an infinity, the first thing you're going to do is replace the infinity with some letter. The standard choice is a b if it's infinity on top, it's a if it's a negative infinity on the bottom. You can pick whatever you want, but I'm going to pick b for the top, a for the bottom, because that's usually what they do in your book. So then we're just looking at this. And then we just kind of just ignore the limit for a while. I'm just going to do that integral like I normally would. I'm going to integrate 1 over x, get the natural log of the opposite value of x. I'm going to plug in the limits of integration from 1 to b. So I get the natural log of b first minus the natural log of 1 second. Notice I did drop the absolute values since b and 1 are both positive. We didn't need them. And then the natural log of 1 is 0. So then I've evaluated that integral as much as possible, right? We've got this. We've got this. And now finally, I'm actually ready to take the limit. And then I have to remember that the natural log function, as b gets larger and larger, the natural log of b also gets very large. It doesn't look very large. Like if you graph the natural log function, it looks like this. But we can see that, oh yeah, as the inputs get bigger, the outputs also get bigger. So the limit of this is infinity, which means the area under this curve is infinite as you go way, 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 way out. I also wrote this over here. So here is shaded in green, the area under f of x equal to 1 over x from 1 to b, and it's just the natural log of b. So as b goes out this way, we get more and more and more and more area, and it happens to be an infinite amount of area. So this integral diverges. To contrast that, we have the integral from 1 to infinity of 1 over x squared. Again, the idea is the same. Or first, when we have an improper integral with an infinite limit of integration, we're going to rewrite it as the limit as b goes to infinity of the integral from 1 to b. So you're just taking that infinity, replacing it with a b, and then saying b goes to infinity. And then I also changed 1 over x squared to x to the minus 2, just because that's easier to anti-differentiate. Sorry, there's a little too much light in here. So then we anti-differentiate x to the negative 2. We get x to the negative 1 divided by negative 1. We still have this limit out here that we have to deal with from 1 to b. I rewrote x to the negative 1 over negative 1 as negative 1 over x. Then I plugged in my limits of integration. I got negative 1 over b minus negative 1 over 1. So I suppose I could have done one more step if you really want. I could have written this as the limit as b goes to infinity of negative 1 over b plus 1. But then we can all see that negative 1 over b is going to get infinitesimally small as b gets infinitely large. So this goes to 0, and you get 0 plus 1, which is 1. So in this case, the area under this curve, y equal to 1 over x squared, is finite. It's not an infinite amount of area, right? It is getting larger and larger and larger, but it's bounded by 1. So if you look at this, right, this green area here, the area under the curve from 1 to b is 1 minus 1 over b. So as the b values go further and further out, the area becomes closer and closer and closer to a value of 1. So we say that this integral from 1 to infinity of 1 over x squared dx converges. And it converges to the value that it's equal to. So these are the basics of convergence and divergence, right? But it's always the same sort of process. You take a limit, you replace your infinity with the letter that you're using for the limit, then you just integrate as normal, and then when you're done, you then evaluate the limit. You say, okay, well, I've got my integral now with my limits of integration plugged in, then I'm actually going to ask what happens as b goes to infinity. So let me pause and ask if you guys have any questions about either of these two examples. For those of you that just came in, we just talked about how the integral from 1 to infinity of 1 over x squared is convergent. It converges to 1. We also talked about how the integral from 1 to infinity of 1 over x is divergent. There's an infinite amount of area, even though it looks like it's like it is getting smaller and smaller as you go out, but it's just not getting small quite fast enough so that the area is convergent. It's a divergent amount of area. There is an infinite amount of area here as you go out to infinity. Whereas here there's a finite amount of area because this function gets small fast enough for the area under it to be convergent. Okay. Yeah, gross. Okay. There is one other thing I really have to make myself say because I saw it in class and I can't ignore it. So she did say something that's true almost all the time. And it's going to be true, I'm sure, in any instance you guys encounter. But there is one thing I need to clarify. And then we'll do examples all day long. So the thing I need to clarify is this. It is true that the integral from negative infinity to infinity of f of x dx is equal to 0 if f of x is odd, with one kind of extra condition. And the extra condition is assuming it's convergent. So the issue is, and I feel like she didn't really say a lot about this, but I'm going to say something about it. So if you have an integral like this, the integral from negative infinity to infinity of, let's actually, I'm going to come back to this, but let's actually look at an easier example. So how about this? How about the integral from 0 to infinity of e to the negative x dx? Well, we're going to do the usual thing. We're going to write it as the limit as b goes to infinity of the integral from e to the negative x, 0 to b dx. And we're going to integrate. The integral of e to the negative x is e to the negative x divided by negative 1, or just negative e to the negative x. This is going to be the limit as b goes to infinity of negative e to the negative x from 0 to b. Here is a pro tip. Rewrite your powers so that they look like they're positive, right? Instead of writing it as the limit as b goes to infinity of negative e to the negative b minus negative e to the 0, I personally, you might not, I personally find it challenging to think about what e to the negative infinity is going to be. That's just not one thing my brain likes to comprehend. It is much more sensible for me, and probably for you, to think of it the following way. It's the limit as b goes to infinity of -1 over e to the positive b, instead of negative e to the negative b. Minus a minus is plus, and e to the 0 is 1. So here's what I'm going to do this every time. I'm going to try and make it so, well, actually it requires looking at two things really. It requires looking at where your limit is going to, right? It's going to infinity, and what your power looks like. So if I can see that putting this down here is going to make this line e to the positive infinity, I like it that way. And I like it that way because I know that e to a really big number is a really big number. And so 1 divided by a really big number, or so -1 divided by a really big number, is a really small number. So I like to think about, am I dividing by a big number or not? And then +1, so this is going to be 0 plus 1. So this integral converges. Okay, let me ask the same question, except now we're going to do the integral from -infinity to 0 of e to the negative x. Let's take a look. This is equal to, so I'm going to cut a corner or two here. This is going to be the limit as a goes to -infinity of, so we know the integral is already -e to the negative x. Let's do this -e to the negative x. We already integrated it. And the limits of integration are going to be, instead of -infinity to 0, they're going to be a to 0. We plug in, we get the limit as a goes to -infinity of -e to the 0 minus a minus e to the negative a. Okay, so check this out. Sorry, now I'm almost out of room here. This is equal to the limit as a goes to -infinity of -1 plus, now here's the thing. This one I am going to leave as e to the negative a. Because a is going to -infinity. So e to the negative infinity is e to the infinity. I like my power to always be a positive, not a negative. So here when I'm plugging in -infinity, I'm getting negative, which is positive infinity. And e to the infinity, e to a big number, is a big number. So this is -1 plus infinity, which is infinity. So this integral diverges. So why does one side diverge and one side converge? Well, let's look at the graph. Yeah. I'm still going to come back to this. So the graph of e to the negative x looks like that. And I think that makes it seem perfectly rational that, of course, this side, the area under here, could converge. And it seems also not unreasonable. Well, of course, this is divergent, right? That's obviously going to be an infinite amount of area. It's huge. So the question then is, what about the integral from -infinity to infinity of e to the negative x? Well, when you have a -infinity and an infinity, you have to split it up. And you can split it up anywhere you want in between those two numbers. The usual choice is 0, unless there's a good reason to pick something else. So we would write this as the integral from -infinity to 0 of e to the negative x dx plus the integral from 0 to infinity of e to the negative x dx. But we just did those. And we found that this one converged and this one diverged. So if you have a divergent thing plus a convergent thing, what happens? Well, sorry, can you speak up a little?
It's still divergent.
Right, it's still divergent. And that's always the case. So here's what I want to say, and this is really kind of important for the next thing I want to say. if you have an integral from negative infinity to infinity, you have to break it up. Then you break it up. If one piece diverges, you're done. The whole thing diverges. You don't have to check the other piece at all. So for this one, since this piece diverged, we didn't even have to think about what was going on over here. Sorry, someone just said something. So this integral diverges. Okay, so why is that important? Well, it's because you could have something like this that diverged. That's why so again, I don't want to focus too much on this because I don't think it's going to come up really, but I just want to point out one thing and then we'll move on. That's not a good example. That's a dumb example, James. The integral from negative infinity to infinity. I'm going to pick a real easy example of like, sure. Ooh, that's a dumb example. Ooh, that's a terrible example. Sorry, I'm thinking of all the worst examples now. Yeah, sure. I have something like x over x to the fourth plus 1. This converges. And it converges because the function's odd. I mean, that's one, well, in fact, it converges, I should say, to 0. That's an odd function, right? F of x equals x over x to the fourth plus 1. F of negative x is negative x over negative x to the fourth plus 1, which is negative x over x to the fourth. Right, so f of negative x equals negative f of x, that means the function's odd. So this definitely converges to 0. Okay, here's the thing I'm going to say that's going to kind of suck. Odd function, for sure. This integral diverges. Because you've got an infinite amount of area under one side. So here's the problem. If you break this up, right? So you've got all this area here and all this area here. Even though these look like they cancel out, no bueno, no good. So the problem here is like if you break this up as the integral from negative infinity to 0 of x cubed plus the integral from 0 to infinity of x cubed, this diverges. Now we're done. One thing diverges, the whole thing diverges. So it would be nice if we lived in a world where we got to say that these canceled out, but it's not necessarily true that this infinity and this negative infinity cancel each other out. Infinity minus infinity is an indeterminate form. It can be anything. So again, I don't really think she'll ever ask you about this because she didn't talk about it at all, but just be aware that it's not always true that this kind of integral of an odd function always is 0. It's 0 if it converges, but it could be divergent. Okay, rant over, just had to, not a rant, so it's just, I really wanted to clarify that because I don't want you guys to think the wrong thing, right? I don't want you to think that this is always convergent to 0. It is if it converges, but it could also diverge. Okay. All right. So now let's get into some funky examples. Let's look at something like, where'd you go? I had a good one here. Yeah, let's look at the integral from e to infinity of, sure, 1 over x times the natural log of x squared dx. Sure. Yeah, let's do the natural log of x to the fourth. Okay, so word of advice. Well, actually, I mean, all the words I'm saying are words of advice, right? You should always start off by doing the limit part. So this is going to be the limit as b goes to infinity of the integral from e to b of 1 over x natural log of x to the fourth dx. Okay, but here's the deal. I don't want to be writing this limit 5 or 6 times as I do this integral. So what I recommend, unless the integral is super straightforward, like the ones we did, like the first ones we did, right? The integral of 1 over x we know is natural log of the absolute value of x. The integral of 1 over x squared we know is negative 1 over x. If it's something really straightforward that you can integrate in one shot, fine, keep going. But if you can't, and a lot of them we can't, I recommend off to the side doing the indefinite integral. So I'm going to do the integral of 1 over x times the natural log of x to the 4th dx. Just off to the side. So I need to do a u sub here, which also, so I know I said before, I always recommend changing the limits of integration for a u sub. I always recommend changing the limits for a u sub unless it's an improper integral. Then I would not recommend it. And I'll talk about why in a second here. So I'm going to let u equal the natural log of x. And my du dx is 1 over x. So my du is 1 over x dx, which is great because I have a 1 over x dx. So I'm going to rewrite this as the integral of, well, 1 over x dx is du, and natural log of x is u to the 4th. So I'm integrating u to the negative 4th du. That's just a power rule. That's going to be u to the negative 3rd over negative 3. Or as I would probably prefer to write, negative 1 over 3u to the positive 3rd. Which then I should plug back in the natural log of x. This is negative 1 over 3 times the natural log of x cubed. Sorry, I know that's kind of scrunched in there. Right. So then I can just go over here and say, okay, that's going to be the limit as b goes to infinity of, there's my antiderivative, negative 1 over 3 natural log of x cubed from e to b. You could change the limits of integration if you really wanted to. Or like you could say it's negative 1 over 3u cubed. And then if x is e, u is the natural log of e, which is 1. The part I have a hard part with is basically, so if x is b, then u is going to be the natural log of b. I think it just feels funky to me. So do what you want, but I personally think it's better to try and stay with the variables we're using. So then we're going to plug in b. We're going to get the limit as b goes to infinity of negative 1 over 3 times the natural log of b cubed minus negative 1 over 3 times the natural log of e cubed. Natural log of b gets infinitely large, so negative 1 over something infinitely large is 0. So then I get plus 1 over 3, and the natural log of e is 1, so I get 1 over 3. So this converges to 1 over 3. If you've got questions, don't hesitate to pipe up. Look at some other hard questions. Let's look at some of these really ridiculous ones where you have a u sub and integration by parts, because those look terrible to me. Oh, yeah, I want to say that too. Sure, let's look at something like this. Yeah, let's do the integral of, what have we got here? Sure. X to the 20th times e to the x to the 7th dx. That would be terrible. So yeah, we'll do this one. Maybe we'll talk about improper. Yeah, maybe. We'll see. So this problem specifically says first do a U sub, then do integration by parts. So what's the U sub choice? Well, as far as I'm concerned, there's only one good candidate. The thing inside the exponent, right? The thing that is stuck. So I'm going to try picking. So normally I would use U, but since they told me I also am going to have to do integration by parts, I really like to reserve the letters U and V for the integration by parts. So I'm going to do a U sub and use a different letter. I'm going to do a T sub. Let's do a T substitution. We're going to let T equal x to the 7th. And then our dt dx, right, instead of du dx, is going to be 7x to the 6th. So I don't have a 7, but I definitely have an x to a 6, or I have x to the 20th. It's definitely x to the 6th, right? So I'm going to have, let's see, 1 over 7 dt equal to x to the 6th dx. Okay. So then we have to try and rewrite everything in terms of t. So what have we got here? What do we got? Do we have a good pen? Yeah, there we go. So the kind of key thing here is to say, look, I need an x to the 6th dx. So I'm going to rewrite this x to the 20th as x to the 6th times the leftovers. So this is going to be, let's see, x to the 6th times x to the 14th is the leftovers. I'm going to put it very suggestively as x to the 14th over here, and then the x to the 6th over here with the dx. Because I know I want the x to the 6th with the dx. And then I still got e to the x to the 7th. Okay. There's my dt. Sorry, my 1/7 dt. There's a t right there. But then we've got this leftover x to the 14th. This is where we have to do what's called a back substitution, just meaning that you have to look and see, well, I know that t is equal to x to the 7th. So I can definitely say, well, that's x to the 7th times x to the 7th, which I'm just going to plug in t equals x to the 7th and get t squared. So I don't know how you want to do it exactly. You might say that this is x to the 7th squared, which is just t squared. But the idea basically is once you've dealt with this, there's going to be some leftover x's, and we just have to use our substitution to figure out what those leftover x's are in terms of the new variable that we want our integral to be in, right? When we're doing a substitution, everything has to become the new variable. So we're going to have the integral of, let's see, t squared e to the t times 1/7 dt. And let's put the 1/7 out in front. Okay, so here is something that I feel like you guys should know, even though it probably won't get taught in class. There are 3 types of integrals. There are 3 types of integration by parts integrals that you can use a shortcut method for. And this is one of them. So here's the problem. When you have t squared times e to the t, or t to the 3rd times e to the t, or t to some positive integer power, that's the number of times you're going to have to do integration by parts. So this problem, I'm going to have to do integration by parts twice, which isn't the end of the world. But why would you do that if there's a faster way? So it's true for anything that's t to a power times e to the t times sine of t or times cosine of t. So let me go to the other side for 1 second and show you. Let's do this example on the other side, and then I'll show you the short way. Because I feel like you would want to know this. So here's the long way. If we're going to integrate t squared e to the t dt. Yes, I left off the 1/7. That's okay. So in the first step, right, we're trying to pick our u for our integration by parts. So u, right, if we're using the acronym LIATE, I feel like the A is always hard for people, right? L is logs. I don't have any logs. I is inverse trig. I don't have any inverse trig. A is algebraic, or I'm going to start saying any power of your variable. So do I have any power by variable? Yeah, I have t to the second power. That's any power of my variable t. So, or the algebraic term, as people often call it. So that's going to be my u. And then dv has to be everything else. So u is t squared. dv is e to the t. du is 2t dt. V is also e to the t. So then this integral becomes u times v minus the integral of v du. So e to the t times 2t dt. And then we do it again. So then for this integral here, we're going to let this be our 2t is going to be our u, right? It's the same sort of choice. And there's my dv. So u is 2t, du is 2, dv is once again e to the t, dt. Sorry, I forgot my dt here. And v is e to the t. So rewriting this, I'm going to get, so let's see, I've still got the t squared e to the t minus the ultraviolet super voodoo. So u times v, so 2t e to the t minus the integral of v du, which is e to the t times 2 dt. But now we can integrate this, and we'll get t squared e to the t minus 2t e to the t minus a minus is plus 2e to the t, because the integral of 2e to the t is 2e to the t. Plus c. Okay, that's kind of a lot of work. I would love to show you a little faster way to do it. Here's the fast way. This is called tabular integration. And I'll once we finish this, once we do this example, I'll say more about it. I'll tell you when you can use it. There's only 3 times you can use it. So for tabular integration, you make a table or columns with your u and your dv. So u, our choice for u in the first integral was t squared. So on the u column, you write all the derivatives, all the way down to 0. So this is why you have to be picking u to be t to a positive integer power. Because this kind of thing, right, where you have x to a positive integer power, that's the only kind of function whose derivative is eventually 0. Any other kind of function, the derivative just keeps going and going forever and ever and ever. But polynomials always have derivatives that are eventually equal to 0 if you take enough derivatives. So the derivatives here are 2t, 2, and 0. And then for your dv column, it's the antiderivatives, which makes sense, right? Because we're doing u and dv, right? We're taking the derivative of u and the antiderivative of dv. So the antiderivative is e to the t, e to the t, e to the t, e to the t until the cows come home. And you want the same number of rows for each thing. And now the final result is super nice. Picking up the wrong pens, yeah. So what we get is this times this. I should really say plus this times this, minus this times this, plus this times this. These signs always alternate. You start with a plus, and then it's just that times that, minus that times that, plus that times that. So in this case, it would be t squared times e to the t minus 2t times e to the t plus 2e to the t. How about that? It's the same thing. You do not have to use this. You might want to, like, if you're using this explicitly showing work on a test, you might want to check ahead of time with Karana that she's okay with you using this, because some people are like, I didn't teach it to you, so you shouldn't use it. I don't really think she's like that, but still good to check. But what I will say is this is definitely a time saver when you have an interval like this. So back to the question we were doing. So we just found this integral. So our actual answer is 1/7 times t squared e to the t minus 2t e to the t plus 2e to the t. And then to finish the problem, we have to go back and substitute in what t is actually equal to, right? Because since this is an indefinite integral, our answer needs to be a function in the same variable that we started with. So I have to go back and plug in x to the 7th for every t. So I'm going to get 1/7 times x to the 7th squared is x to the 14th times e to the x to the 7th minus 2x to the 7th e to the x to the 7th plus 2e to the x to the 7th. Whew. Good times. What time is it? Okay, we got 13-ish minutes. I think we're doing all right time-wise. Yeah. So questions about this before I say a few more words about tabular integration. Just a few, though. Okay, you can always ask questions. Never mind. So here are the 3 situations where you can use this idea. If you're integrating x to a positive power times e to the x, or really e to the any, right? You could have a coefficient here that's fine. X to a positive integer power times sine of x, or x to a positive power times cosine of x. These will all lend themselves to being done via tabular integration. So for example, we could integrate x to the 4th times cosine of x. And here's how it's going to work. Our u is going to be x to the 4th. And then we're going to take all the derivatives. 4x cubed, 12x squared, 24x, 24, and 0. This problem, by the way, you'd have to do integration by parts 4 times if someone asked you to do this problem. It's not fun. And then your dv here. So for cosine and sine, your dv you have to be a little more careful with. Right? For e to the x, it's easy, right? It's the antiderivative e to the x, e to the x every time. For cosine of x, remember we're taking the antiderivative. The antiderivative is sine of x. And the antiderivative of sine is negative cosine. And the antiderivative of negative cosine is negative sine. And the antiderivative of negative sine is positive cosine. And the antiderivative of positive cosine is positive sine. So then it's plus this times this, minus this times this, plus this times this, minus this times this, plus this times this. So our final answer for this integral would be long and terrible to write, but it would be x to the 4th times sine of x minus 4x cubed times negative cosine of x. I should really just make that plus, right? It's plus 4x cubed times cosine of x. And then plus a minus, I'm going to get a minus 12x squared times sine of x minus 24x times cosine of x plus 24 times sine of x. So much faster than actually doing the process of doing integration by parts 4 times in a row. So keep this in mind. It's definitely worth using if it comes up. All right, what else can I look at? Oh yeah, let's look at that problem. Let's look at, what do I got here? Let's go back and do a couple more. Oh yeah, we should do a couple more improper things. So here's problem 7, the other half of problem 7 from your homework. I'm going to change it up just slightly. Let's do the integral from, let's do the integral from 0 to infinity of x squared e to the minus 3x. Okay. This one, nah, I'm making it. I feel like I'm making it slightly harder than it really needs to be. Let's just make it x to the negative 3x. This one you could use tabular, but it's also just a one integration by parts integration. So I don't think you really need to use the tabular method that we just talked about. I know I'm going to do a limit, right? I have to do a limit as b goes to infinity of the integral from 0 to b of x e to the negative 3x dx. So then, right, we do the antiderivative off to the side. My u is going to be x. My dv is going to be e to the negative 3x. My du is going to be 1 dx. And my v is going to be the antiderivative of e to the negative 3x is e to the negative 3x divided by negative 3. And I forgot my dx here. Sorry about that. Actually, if you notice this really is just tabular. It's just a one-step tabular. Because you're going to get, yeah, you're going to get this times this minus this times the antiderivative of that. It's kind of cool. I'll tell you what I mean when I say that, right? So if I was making my tabular, my tabular list, if I had u, it'd be x, 1, 0, and my dv would be e to the negative 3x. The antiderivative of that is e to the negative 3x divided by negative 3. And the antiderivative of that is e to the negative 3x divided by negative 3 times another negative 3, which is 9. So when we do this, we end up getting, either way, sorry, now I'm kind of saying a lot here. Either way, we're getting x times e to the negative 3x over 3 minus the integral of v times du, which is e to the negative 3x over negative 3 dx. And that's going to equal x e to the negative 3x over negative 3 minus a minus, so plus 1/3 integral of e to the negative 3x. But we know what that is. It's just another e to the negative 3x over negative 3. Which is exactly what you would get if you did the tabular thing. Right? You would get x times e to the negative 3x over negative 3 minus 1 times e to the negative 3x over 9, which is exactly what you're getting here. Cool. Okay, so then we use this to deal with this. So this is going to equal the limit as b goes to infinity of this mess here. And I'm going to rewrite this a little bit. I'm going to rewrite this as negative x on top and 3e to the positive 3x on the bottom. Same deal here. I'm going to write this as minus 1 over 9. And then the e to the 3x in the denominator from 0 to b. I have to erase somewhere. I guess it's going to be down here. So we end up with, so now we're plugging in on some integration. We get the limit as b goes to infinity of negative b over 3e to the 3b minus 1 over 9 e to the 3b minus, and then we plug in 0. We get 0 over e to the 1, e to the 0, minus 1 over 9 e to the 0. So 1 over 9. All right. She did something kind of interesting in class where I think she got like a common denominator for this piece here, which is totally fine. In fact, it's not that terrible to do. And yeah, I think actually it's probably the best way to do it. So I'm going to multiply this by 3 over 3. Now I've got the limit as b goes to infinity of negative 3b minus 1 over 9e to the 3b plus 1/9. Okay. The limit of this is 0. But what I'm pretty sure she wants you to do, or at least to think about, is the fact that this is an infinity over infinity form. Right? The top is going to negative infinity. The denominator is going to positive infinity. And when you have an infinity over infinity, you have to use L'Hopital's rule. So if you use L'Hopital's rule, the derivative of the top, negative 3b minus 1, is just negative 3. The derivative of the bottom, the derivative of 9e to the 3b is 9e to the 3b times 3. And then this just sticks around, right? This is kind of on its own. Well, now this is clearly 0 because the numerator is negative 3 and the denominator is infinitely large. So this is going to be 0 plus 1/9, which is 1/9. And this comes up a lot, this L'Hopital's rule thing. Whenever you're doing like an improper integral and you've got like an x times an e to the x or something of that nature, you're pretty much always guaranteed to have a L'Hopital at the end here. Yeah, I know it's nobody's favorite thing ever, but oh, I'm mistaken. I do see at the end of the homework one problem that is the other kind of improper integral. So let's do one of those. I'm glad I saw that. So not every improper integral has an infinity. You can definitely have an improper integral that is undefined somewhere on the interval. For example, let's say I was doing the integral from, yeah, let's not make it terrible, from 0 to 8 of 1 over the cube root of x. So the problem with this is on this interval, if you plug in 0, 1 over the cube root of 0 is 1 over 0, which is undefined. So here we're going to write this as the limit as a approaches 0 of the integral from a to 8. And I'm going to rewrite this so that it's easier to anti-differentiate. Instead of writing it as 1 over the cube root of x, I'm going to write it as x to the negative 1/3. Now, I didn't actually write this exactly right. It's mostly right, but technically, when you're not dealing with infinity as one of your limits of integration and you have an improper integral, I'm between 0 and 8, right? This integral is from 0 to 8. And none of this other stuff matters. So let me ask you, if we're between 0 and 8, what side of 0 are we on? Are we on the right or are we on the left?
Left.
0 is the left, but we live here.
Right.
Yeah, I mean, right, it's not left, it's gotta be right, right? So yeah, we are on the right side of 0. And so people usually write this as the limit as a approaches 0 from the right. It's not a huge deal. No one probably ever really cares, but it is something you will see people do all the time. So if you have an integral like this, the lower, if it's on the bottom, you're always approaching it from the right. And if it's the one on top, you're always approaching it from the left. Because if 8 was what we were replacing, we'd be like, oh, I'm on the left side of 8, so I'm approaching from the left. So, and then we would just treat this as usual. We would the limit as a approaches 0 from the right. We'd integrate this. We get x to the positive 2/3 times 3/2, right? We add 1 to the power, divide by the new power. From 0 to 8. And now here's the thing. Well, actually, let me say that. I know we're out of time, so let me just finish this up here. So limit as a goes to 0 from the right. I'm going to have 3/2. Oops, I made a small mistake. That shouldn't be a 0, that's an a. It's easy to accidentally have your a turn into 0. So this is 3/2 times 8 to the 2/3 minus 3/2 times a to the 2/3. And now here's what happens. A goes to 0. And 0 to a positive power is just 0. So this part's perfectly okay. So we're going to get this minus 0. So we're going to get 3 halves times 8 to the 2/3 is 4 minus 0. So that's going to be 6. So this converges. So if the problem in your original integral was that you were dividing by 0 somehow, because you have like x to a negative power, and then when you integrate, you end up getting x to a positive power, you're probably not going to be dividing by 0 anymore.